So welcome to week 8, everybody. I'm not positive, but I'm thinking this might be our second to last week. Although that being said, it will be kind of another knowledge-based week, and we will be spending probably the next week really attacking the congruent number problem using everything we've learned. So I don't want to say a whole ton about Heck operators because they're a little bit tedious, but it really boils down to the fact that there's these operators called the Heck operators that sort of act as linear maps between spaces of modular forms, for congruent subgroups gamma 1 of n, and they also preserve the space of cusp forms within those spaces of modular forms, and they have very powerful structural implications for those spaces. And it turns out what we're really going to need is the concept of an eigenform later, which is just like a modular form that acts like an eigenvalue for all of the different Heck operators at once. So that's really one of the structural things that we're going to be using in the future. In particular, we're going to want to know that for certain spaces of modular forms, there's actually a basis of normalized eigenforms. And we've already talked about that a little bit. For example, I told you, I think we have 2 results along those lines. So there's always a finite basis of eigenforms for all Heck operators for the space S sub k of n chi for any character chi, as long as the index of the Heck operator is co-prime to the level. And then as a matter of fact, this also holds for the space of new forms, even if you remove the condition that lowercase n and uppercase n are prime to each other. Okay, so Heck operators are structurally important. We're going to want a basis of them for certain spaces as we move forward. So today, what we're going to want to do is we're going to want to somehow define modular forms of half integer weight. And this is the last type of modular form that we're going to need to define. We've already defined several types of modular forms. Modular forms for all of SL2Z, modular forms for all the various special subgroups of SL2Z, modular forms with respect to a Dirichlet character mod capital N, and so on and so forth. So now we're going to do modular forms of half integer weight. And to do this, we're going to have to require and recall the functional equation for big theta. Remember, big theta is the function. It's the sum over the integers of q to the n squared, where q is the typical variable e to the 2 pi I z. If you recall, this had a very non-trivial functional equation. Big theta of gamma acting on z is the so-called automorphy factor j of gamma z times big theta of z. And what was this automorphy factor, j? It was the Legendre symbol c over d times this epsilon sub d, reciprocal of epsilon sub d times radical cz plus d. And I don't know why I didn't write it, but I believe epsilon sub d is, if you recall, square root of Legendre symbol -1 over d. And c and d are, of course, as usual, the entries in the bottom row of the matrix gamma. And where is gamma living? For which gamma does this functional equation hold? All gamma in gamma naught of 4 and all z in the upper half plane. So this was a huge result that we had. I probably didn't make it sound very huge because I just really stated the result and didn't do the proof, but the proof is quite difficult actually. So, okay, so motivated by this functional equation, what we're going to do is anytime we have an automorphy looking condition like this, so f of gamma of z equals cz plus d to the k times f of z for some integer k, kind of like, shows up in the definition of modular forms, we're going to actually call this cz plus d to the k an automorphy factor, kind of like how the little j up here is an automorphy factor. Okay, and usually that's denoted by capital J of gamma z instead of lowercase gamma z. We reserve lowercase j for the automorphy factor of big theta. And gamma just lives in some matrix group, let's say. We don't want to be too restrictive about that. So anytime we have a condition like this, our cz plus d to the k guy, that's going to be called an automorphy factor. If you want a little exercise, you can show that for any automorphy factor, j of alpha times beta z is j of alpha comma beta of z times j of beta z, where alpha and b are just any two matrices in your whichever matrix group you're working with. And then you might also always try to figure out what j of -1 comma z always equals, where -1 is just shorthand for the negative of the identity matrix. Okay, so we don't need those results, but it's a good little exercise to try. So if you look, we talked about this before, but if you look up here at the functional equation for theta, and then you actually really look at what little j is, what do you notice? You notice that you've got the square root of cz plus d. So that's kind of like, well, it's not kind of like, it's just cz plus d to the 1/2, which is very much what you might expect if you were able to define modular forms of half integer weight. You would expect the automorphy factor here to look like cz plus d to the k/2, where k is some integer. In the case k equals 1, you would get exactly this square root here. And then you look at this here, this c/d times epsilon d to the -1st. That seems complicating, but in principle, it's not really, right? Because c/d is just always ±1. It's just some nice unit, and 1 over epsilon sub d is just, plus or minus I, plus or minus 1, something like that, depending on the situation. So these are really just like 1, -1, I, -I, something like that, times, a very nice expected automorphy factor looking expression. So we shouldn't be too disheartened by the presence of these things. And so what we're going to ideally want moving forward, keeping that in mind, is if we're going to define half integer weight modular forms, F, we ideally want them to satisfy something that kind of looks kind of like this. F of gamma z equals cz plus d to the k/2 times f of z, for z in the upper half plane, and for gamma probably in some congruent subgroup. And then there might be times some plus or minus 1, plus or minus I, some expression out there that yields something of norm 1 in the complex plane. Okay, there might be something else, so times some norm 1 constant. Okay. Now, so that being said, if you just try to require this without any constants out front, if you just say, okay, I'm going to want f to satisfy this exact expression right here, that doesn't really work because there's 2 branches of the square root, right? And so you might guess, well, okay, why don't we just fix the standard branch of the square root then? The one that takes positive reals to positive reals, and the upper half plane to quadrant 1 and the lower half plane to quadrant 4. Does that fix the issue? No, it doesn't. In fact, I'll leave it as an exercise that you can show that even once you fix a branch of the square root, this naive automorphy factor here can never actually be an automorphy factor for any non-zero function of any congruent subgroup. It's probably a little bit of a tricky exercise, but the short story is this doesn't work, even if you fix a branch of the square root. Okay, but there is a way around it, around this problem. And the way around it is we have a good looking functional equation that looks automorphic already for big theta. So here's what we're going to do. Where did that work for, by the way? We got to keep that in mind. This worked for all matrices in gamma naught of 4. So for gamma naught of 4 or any congruent subgroup inside of it, of course, there's a workaround. What we can do, since this little j looks so much like our standard automorphy factor for k equals 1, we're just going to go ahead and say, all right, for this congruent subgroup, I'm going to define the automorphy factor to just be the kth power of little j. That's it. So I'm going to take the kth power of this expression here, and I'm going to require that hopefully, that half integer weight modular forms satisfy an automorphy condition with this as the automorphy factor, maybe raised to the k power. Okay, so in other words, you at least want a modular form of weight k/2 for some congruent subgroup of gamma naught of 4 to be a holomorphic function on the upper half plane, as usual, with the above automorphy factor raised to the k power. So raised to the k power, I got to fix that. Okay. And then as usual, we might want to compactify this notation down because this can become cumbersome to write over and over again, but we're going to define f bracket gamma sub k/2 to be exactly what you would expect it to be, if you remember what f bracket of gamma sub k was before, it's just going to be the automorphy factor raised to the negative k, the automorphy factor for big theta, that is, times f of gamma of z. This is exactly the same as the definition we had for the bracket notation before. And gamma, again, will just be in big gamma not of 4, and k will be odd, because if k is even, then this is, not really a true half integer weight modular form, because k over 2 will just be an integer. We might as well talk about regular modular forms in that case. Okay, so rewording that yet again, what we could say is, we at least want modular forms of weight k over 2 for k odd to be holomorphic functions on the upper half plane that are invariant under bracket gamma sub k over 2. Okay. Now, if you remember back when we defined modular forms for the full SL2Z and for congruent subgroups, we also wanted to define similar notions for more general matrices that didn't necessarily live in SL2Z. Maybe they live more broadly in the bigger matrix group GL2 plus Q. The real problem, though, is when you try to just port this all up to GL2 plus of Q, there's no preferred branch of the square root in this group, because the automorphy factor was only defined for gamma and big gamma not of 4. There is a way around this. I'm going to give you just a few of the details just so you have some sense of what's going on. But basically, instead of working in GL2 plus of Q, you're going to work in like a 4-sheeted cover of it in some sense. What do I mean by that? Well, the first thing is you're going to have one copy of GL2 plus of Q for each branch of the square root. So that's kind of like a 2-sheeted cover of GL2 plus somehow. But then that's not enough, because if you look at the toy case of big theta, for example, you see that you want to include both roots not only of CZ plus D, but of negative CZ plus D, because the automorphy factor little j is actually the square root of this expression here. Of Legendre symbol negative 1 over D times CZ plus D. So you need roots also of negative CZ plus D, because this Legendre symbol could be negative. So that's going to introduce another expression, which itself has 2 square roots. So you're going to end up having to work with kind of 4 copies of GL2Q at once. Okay, and so let me be a little bit more precise about that now. We're going to let capital T be the set of the plus or minus 1 plus or minus I. Okay, and we're going to define G, our group that we're going to work with, to be the following. It's not just going to be elements of GL2 plus Q like we've gotten away with in the past. It's going to be the set of pairs alpha phi of Z, where alpha, yes, lives in GL2 plus of Q. That's fine. But then for every alpha, there's essentially going to be like 4 of these phi functions. And what are these phi? They're holomorphic functions on H, such that when you square them, you get kind of the square of the typical automorphy condition looking thing, times maybe some T, where T is plus or minus 1. Okay, so if you square rooted, there'd be 4 possibilities. There'd be plus or minus 1, plus or minus I. So there would be 4 coordinate pairs per matrix in GL2 plus. And so I wrote that here. So for each matrix, we admit 4 pairs like we wanted, and we've now taken care of all the possible branches of all the square roots of all the different expressions that we could possibly want to consider when defining automorphy. And so we're good to go. And you can even show G as a group. It's no big deal. Here's the multiplication. If you want to do A phi of Z times beta psi of Z, you just do, I'm sorry, I said that wrong. If you want to do alpha phi of Z times beta psi of Z, the multiplication will be defined to be alpha beta, comma, phi of beta Z times psi of Z. You can show that's a group law, okay? And you can also show that phi is always a constant whose image is a 4th root of unity, right? And what all this leads to is the following observation. Despite all this relatively complex structure up here, there's a certain isomorphism that's going to make this all very understandable and practical and workable and tenable for us. So for the general case, so for any element of big G now, so not necessarily in SL2 or any congruent subgroup, not necessarily in GL2 plus of Q, but in this big 4-sheeted cover of GL2 plus, we're going to define a bracket notation. That was the whole goal after all, right? Was to define some kind of bracket notation for more general matrices. And it's going to be kind of exactly what you might expect it to be. It's going to be f of alpha acting on z, sort of like up here in the original bracket notation definition. And then we should have times some automorphy factor looking thing to the negative k, because that's what we had up here. But the natural choice for the automorphy factor is this phi of z here, because it looks, when you square root, or when you square, well, yeah. So when you look at this expression here for phi squared, it looks so much like the square of an automorphy condition, times maybe some complex number of norm 1, okay, which is fine. And that's exactly what you're going to do. You're going to define f bracket zeta for zeta in G to be exactly this automorphy condition looking thing here. And then, because this is all kind of working under the umbrella of big gamma naught of 4, whenever you have a congruent subgroup in there, let's say gamma prime, you can define gamma prime tilde to not just be, don't just take it to be all the elements of gamma prime. That's the naive thing to do. That doesn't work. We just saw that doesn't work. Instead, take all of the pairs from G whose first coordinates live in gamma prime, comma, the original little automorphy factor for big theta, little j of gamma of z. And when you do that, you can actually show that gamma naught of 4 is isomorphic as groups to gamma naught tilde of 4. It's just that this makes a whole lot more sense because it takes everything we want it to into consideration under the umbrella of this big G here. So there you go. So we're able to fix the square root branch problem basically in a way that allows us to do things a little bit more generally than just living in SL2Z. So we can, in particular, we can define the bracket notation for matrices outside of SL2Z in a way that when we restrict back down to the gamma naught of 4 case, we end up with a nice isomorphism of groups. Okay, now I'm going to do a little bit of hand waving, although secretly I've been doing hand waving this for the last 7 weeks, but you should expect that we aren't quite ready to define modular forms of half integer weight, even for subgroups of gamma naught of 4. Why? Because being a modular form always has 2 conditions attached to it. Some kind of automorphy condition, right? And then some kind of meromorphicity at the cusps condition, or holomorphicity or vanishing at the cusps condition, depending on whether or not you want to be a modular function form or cusp form. There is a way to do that for half integer weight modular forms, and I'm just going to tell you that it works and there's a way to do it. And I will also tell you that, much like you might expect if you've been paying attention over the last several weeks, it does involve a certain Q expansion looking series only having finitely many negative index terms, or no negative index terms if you want to be a modular form, or a vanishing 0 index term if you want to be a cusp form. Okay, just like in the ordinary modular forms case and in the congruent subgroup case. Okay, so I'm not even going to write that condition down because it's very ugly and it takes a little while to derive. So just trust me, there's some other condition you want as well. So now we're ready to define modular forms of half integer weight. And here's what we're going to do. Okay, we'll be an integer. We're going to take, this is only going to work for congruent subgroups of finite index in gamma naught of 4. Okay, the finite index kind of pops up later, by the way. And again, I mean, we want F to at least be meromorphic on H to even start talking about this, just like in the previous cases. So what we're going to require is that F be invariant under this bracket sub k over 2 of gamma tilde for all little gamma tilde and big gamma prime tilde, where that was defined above. Okay, then we're going to say F is a modular function of weight k over 2 for the tilde version of that congruent subgroup if it satisfies this mysterious meromorphicity condition at the cusps that I didn't define up here. And it will be holomorphic on H. If it is also holomorphic on H and at every cusp, then we'll call it a modular form, just like usual. And we will write in that case that F is an M sub k over 2, not of gamma prime, but of gamma prime tilde. Okay, so we want to be working under this 4-sheeted GL2 plus cover. And then, as you might expect, If in addition, f vanishes at every cusp, whatever that means, then we will call f a cusp form, and we will write that f is an s sub k over 2 of gamma prime tilde, right? So the key is there's this power series condition I didn't write down, and then we also want invariance under bracket gamma tilde for all little gamma tilde and big gamma prime tilde, just like you would expect. Okay, once you have done this, you can get a bunch of really quick facts out of the way that are akin to the ordinary and congruent subgroup modular form cases. So for example, you can start to define some other spaces, like you can define a half integer weight modular form with respect to a Dirichlet character, which is something we're going to need to do. So if capital N is 4K, that condition just guarantees that gamma naught of big N is in gamma naught of 4, because this all only works under the umbrella gamma naught of 4. And chi is a Dirichlet character mod N, then we're going to denote by m sub k over 2 of gamma naught tilde of n comma chi the space of all half integer weight modular forms at level n, like how we defined above. But it's a subspace of that, of the functions that aren't necessarily, they're not invariant under bracket gamma sub k over 2 for all gamma prime in big gamma naught of n, but they're invariant up to some twist by the character chi evaluated at d, where d is, of course, the lower right entry of gamma. Okay, so this is exactly how we defined modular forms for characters before. Now, there is one difference in notation I should make you aware of. Before, we had a similar definition for modular forms for characters, but the notation before was just m sub k of n chi. Here, for some reason, the standard notation is not m sub k over 2 n chi. You don't just write n, you actually write gamma naught of n, which personally, I think this should have been gamma naught of n before, but I just wrote everything down like how it's standard in the literature. So I don't know why they're different, but they are, just so you're aware of that. Okay. And then what do I mean by like half integer weight cusp forms at level n with respect to a character? Obviously, I mean the only thing I could possibly mean, take modular forms for that character and intersect with the big half integer weight cusps for the entire congruent subgroup. There's nothing else you could really mean there. So that's what that would mean. Here's 3, 4, 5, something like that, facts, and you're going to recognize a lot of these as familiar to you if you remember some of this stuff from ordinary modular forms. So for example, we do have a nice direct sum decomposition from representation theory. We know that half integer weight modular forms for gamma 1 tilde at level n can be decomposed into the specific modular forms with respect to all the different Dirichlet characters mod n. Okay, so like before, this direct sum is over all Dirichlet characters mod capital N. Okay, something very similar to what we had in the congruent subgroup case. Here's another interesting thing that actually pops up in a proof of something we will talk about later. If you take, let's say, 2 modular forms, F1 and F2, and you make them half integer weight with weight K1 and K2, and you make them each with respect to a different character, chi sub 1 and chi sub 2, then F1, F2, of course, is going to have half integer weight K1 plus K2 over 2. That's akin to what happens in the ordinary modular form case. But what you might find a little bit interesting is this new modular form F1, F2 is still a modular form of half integer weight with respect to a certain character, and that character is just chi1 times chi2. Okay, so that's nice. A couple other things to be aware of would be if chi is an odd character, which just means it sends -1 to -1, then the half integer weight modular forms at level n for that character are 0. There's none of them, okay, except 0 itself. And another very nice result is this. So let's say chi is, or I'm sorry, let's say we're looking mod 4 now. So instead of just looking mod capital N, let's look mod 4 specifically, because things in the past have tended to work out better for us when we restrict to capital N equals 4. There are two characters mod 4. I've actually already told you that before. There's the trivial character, okay? And then, which is an even character, meaning it sends -1 to 1. And then there's the only non-trivial character mod 4, okay, which we've talked about before. In fact, I've given you an expression for it before, okay? And if you apply this direct decomposition and some of these facts appear and you combine them all together, you get the following. Weight k/2 modular forms for big gamma 1 tilde of 4 are the exact same thing as weight k/2 modular forms for big gamma naught of 4 tilde. Okay, that really follows from this direct sum decomposition and the fact that you get 0 for odd characters. Okay, so that's nice. And both of these are equal to weight k/2 modular forms of big gamma naught tilde of 4 for the trivial character 1. We usually just call 1 the trivial character. So all three of these spaces are exactly the same when you restrict your characters to be of level capital N equals 4. Okay. And to go on and give you the next proposition, I'm going to have to introduce another definition. Surprise, surprise. We're going to have to define this character chi sub -1. It's going to be the character mod capital N, where 4 divides N, given by chi sub -1 of little n is -1 to the n-1/2. I should probably have put parentheses here. Okay, and this is going to be a Dirichlet character mod capital N, so you can think about it as being a character on Z mod NZ star. Okay. Once you have defined this character, you are able to finally see the first of many connections between the world of ordinary modular forms and the world of half-integer weight modular forms. And here's that connection. So let's say 4 divides capital N so that this all makes sense. Okay, now let's suppose that k/2 is an integer. Okay, then in the half-integer weight modular form sense, this group here, m sub k/2 of gamma naught tilde of n comma chi, okay, is equal to, in the ordinary modular form sense, because k/2 is an integer, so I can think of this also as a space of ordinary modular forms. It's equal to that ordinary space of weight k/2 modular forms at level n for the character chi sub -1 to the k/2 times chi. And I guess I didn't write what chi is here, but chi is any Dirichlet character mod n. Chi a DC mod capital N. Okay. So there's this kind of like, because you might ask yourself like, okay, so if I define half-integer weight modular forms, but k happens to be even, what kind of crossover do I get between half-integer weight modular form land and regular modular form land? Are the groups equal, or is there some kind of maybe a little twist by a character going on? The answer is yes, and here's the relationship. Okay, and in fact, you can see down here, this equality respects cusp forms as well. In other words, if I replace capital M by capital S, I get the exact same equivalence. Okay. So what we're doing appears to be okay. We do have to kind of twist our character by this chi sub -1 to an appropriate power, but ultimately that's not such a big deal, right? Because again, you're really just multiplying by roots of unity when you do that. Okay, to end this section, this was a short section. I really tried to keep this short because defining half-integer weight modular forms properly takes a long time. But the last thing that we want to be aware of is, can we classify, it appears that big gamma naught tilde of 4 is a special space. So can we classify all of its half-integer weight modular forms? And the answer is yes, as follows. Define capital F of Z to be the following function. It's going to be the sum over any odd numbers bigger than 0 of sigma 1 of n q to the n. And remember, what is sigma 1 of n? I keep reminding you of this every time, but it's easy to forget. Sigma 1 of n is the sum of the divisors of n. The 1 just refers to the fact that this is a first power here. And remember, what's q? Q is e to the 2 pi iz, our standard q variable. Okay, so this is a nice function. And what you'll do is you're going to act like big theta and big F are variables, and you're going to assign them weight. You're going to assign big theta weight 1/2, and you're going to assign big F weight 2. Okay, then it turns out that this space of modular forms of weight k over 2 for big gamma naught tilde of 4 is actually the polynomial ring over C in big theta and F, but you only want polynomials of pure weight k over 2. And if you do a little bit of thinking for a second, you can actually deduce the dimension of this space from this result. And it has dimension 1 plus bracket k over 4, where bracket means take the integer of largest absolute value less than or equal to absolute value of whatever the number you're taking the bracket of is. Okay. So we can actually kind of describe this as a kind of polynomial ring in big theta and F, which will be important for us later. And we also know the dimension of the space, which admittedly won't be that important for us, but it's cool to know. Okay. So there you go. There's a little crash course on half integer weight modular forms. The next thing that we want to, again, just kind of briefly touch on here is, for half integer weight, or I'm sorry, for modular forms for SL2Z and congruent subgroups, it kind of appears like, or appeared like Eisenstein series were crucial building blocks for those spaces. So is there some kind of Eisenstein series for half integer weight modular forms for this nice special subgroup under whose umbrella we're working? So before we get into that, let me remind you what the weight k Eisenstein series was. We called it G sub k of z, and it was this infinite sum over pairs mn, where m and n were not both 0, 1 over mz plus n to the k, where k was bigger than or equal to 4 and even, and z was in the upper half plane. Okay, if you recall, we actually, this is a weight k modular form for SL2Z, first of all, which means it has a nice Q expansion. And in fact, the Q expansion is completely known. I am not going to cover that again, but I did, for those of you who read the notes, type it up again. This is just copy and pasted from earlier in the notes. Okay. And then we notice this is not quite normalized in the sense that its leading coefficient is not 1, because there's this 2 zeta of k out front, where zeta is the Riemann zeta function. And so you can normalize this, producing E sub k of z by dividing G sub k of z by this 2 zeta of k. Okay. When you do that, you produce E sub k of z, and we call these the normalized weight k Eisenstein series. And I even left it as an exercise before that there's a nice expression for those that looks very similar to the starting expression for G sub k of z. So you look at this and you're like, all right, well, if I'm going to have something that's like as important structurally to the weight k over 2 modular forms, then maybe I'll call that an Eisenstein series, and hopefully it has a form that looks sort of like this. Okay. And it turns out what you want to do is define 2 different Eisenstein series. And I'm just going to give you the definitions and more or less kind of breeze past some of this because it can get a little bit heavy, but you can show that the correct analogous definition for one of the 2 normalized Eisenstein series of weight k over 2, as long as k is bigger than or equal to 5 and odd, is the following. You're going to define it to be E sub k over 2, of course, that would only be natural. And it's going to look a whole lot like what you might expect it to look like. You might expect k here to be k over 2, which it will be. You might expect, because it seems to be par for the course, that we're multiplying by maybe some plus or minus 1s or plus or minus i's out front here. Yes, that does happen. But then more or less, you should expect the rest of the Eisenstein series to look exactly like it did up here. And so here's the definition. You're going to take the sum, again, overall, pairs mn and z, where m and n are not both 0. You do have to require that 4 divides m and that n is positive and that m and n are coprime. But other than that, you end up with this summand. Legendre symbol m over n, epsilon sub n to the k, mz plus n to the negative k over 2. Don't worry about epsilon sub n. That's the exact same thing it was above in the functional equation for big theta. I wrote it up. Where did I write it? Somewhere. Yeah, I wrote it up here earlier. It's the same epsilon from earlier. So we have that. That's one of the Eisenstein series. Okay, but it turns out that because of the way the cusp structure works for big gamma not a 4, there is a need for a second Eisenstein series if you want the Eisenstein series for half integer weight modular forms to provide and serve the same kind of role they did for ordinary weight modular forms. And here's how that looks. We call that second Eisenstein series, that second normalized Eisenstein series, F sub k over 2 of z instead of E sub k over 2 of z. And what that is it's very similar. You'll notice the expressions are almost identical, but there is this 2 to the negative k over 2 out front, first of all. Second of all, you'll notice that what we're summing over is a little bit different. We're not just summing over all pairs in z. We're not requiring any longer that 4 divides m. That doesn't show up here at all. But we get rid of that condition, but n is now no longer just able to be bigger than 0. It has to be bigger than 0 and odd. But we're still going to keep the condition that m and n are co-prime. And then there is a slight change inside the sum as well. There's 2 changes. Instead of Legendre symbol m over n, it's Legendre symbol negative m over n. The epsilon sub n to the k stays the same, but then mz plus n to the negative k over 2 becomes nz plus m to the negative k over 2. But other than that, I mean, if you were just to glance at these, without paying attention, they would look very similar. Okay. I actually think I'm going to, we'll talk about this. Okay. So in the case of ordinary modular forms, like up here, remember the normalized Eisenstein series, we completely understand their coefficients. In particular, we completely understand the Q expansions for the regular Eisenstein series. And here it is. Okay. So you might ask, is there some kind of analogous result for these half integer weight Eisenstein series? And the answer is yes, in the form of the next following 2 propositions. So from now on, lambda is going to refer to k minus 1 over 2. You're going to see that pop up in a lot of propositions from here on out. We're also going to define this expression here. It's like chi, it's like a character, but it's denoted not chi sub negative 1 like before, but chi sub negative 1 to the lambda sub L. Okay, it's a little bit ugly. Its value at n naught is going to be the following product of Legendre symbols. It's going to be Legendre symbol negative 1 over n naught. That negative should be up with the 1 to the lambda power times Legendre symbol L over n naught. Okay, where L is just something. Okay, well, we're going to talk about what L is in a second, actually. And then we're going to bring up an old definition that we already had. The twisted version of the L function of some kind of Dirichlet character. That's what this definition is. So it's L of chi of s, comma s, and it's going to be the sum from 1 to infinity, the character chi evaluated at n times n to the negative s. Okay, and of course the sum is over n. Okay, this is a definition we've already seen before. And of course, this is convergent for a real part of s bigger than 1. We've talked about this before. This is just standard Dirichlet series theory. Okay, so what are the coefficients of my Eisenstein series for half integer weight? Well, you get something kind of remarkable. So let's look at f sub k over 2, the second Eisenstein series first. Let's write its Q expansion as the sum from 1 to infinity b sub L Q to the L. Okay, so now we get to see what L is here. L is ranging from 1 to infinity. It turns out for L square free, there is a known formula for b sub L. And what it is it's this L function where the character chi is chosen to be this character we defined up here, evaluated at which s value? 1 minus lambda. Okay, this is going to be sort of important for us when we start attacking the congruent number problem again, right? Now, it's not just that. B sub L is not just this. You might have to multiply by some scalar, but that scalar will only depend on lambda and L mod 8, but it does not depend on L. It only depends on L mod 8. Okay. So one kind of number theoretic realization that's nice to have moving forward from this is, if I take this lambda here to be fixed and even, okay, then as L ranges through all the square-free positive integers, which is exactly what it's doing in this formula up here, okay, then these characters here that I define that depend on L, they actually range through the canonical characters attached to all the real quadratic fields Q adjoins square root of L. This Q adjoins square root of L, if L is positive, has discriminant capital D, which is little l if little l is 1 mod 4, and 4 times little l else. You need some algebraic number theory here. Don't worry about it too. The only thing I have to tell you is, what is this canonical character? It's exactly what you think it should be. It's just chi sub d, which is the Legendre symbol character. Okay. Right? D over m for m odd. This is also going to be something we're going to use later. By later, I mean, it's actually coming up pretty soon here, but okay, well, that only works if lambda is fixed and even. What if lambda is fixed and odd? Well, then if you let L vary, these characters will now run through all the characters attached to the imaginary quadratic fields, Q adjoins square root of negative L. We know those number fields have discriminant capital D equals negative little l if little l is 1 mod 4, and negative 4l else, okay? And again, the canonical character is still chi sub d in all cases. So it's like you can begin to do some work, a little bit of work pulling from algebraic number theory here once you make this realization. We won't make a lot of that explicit, but what you are going to see from now on in certain results is this chi sub d character is going to pop up. And you're going to just want to keep in mind, oh yeah, d was just the discriminant of some number field. Okay. And so this result up here worked for f sub k over 2. Let me give you a result, one key result that tells you a lot of information about both of the half integer weight Eisenstein series, E sub k over 2 and F sub k over 2. Here's the theorem. So it turns out both E sub k over 2 and F sub k over 2 have absolute value capital D coefficient in their Q expansions equal to this L function up here, where the character is now chosen to be chi sub d, where d is this capital D, this discriminant, okay? Still evaluated at 1 minus lambda, much like in the F sub k over 2 proposition up here, times a factor depending only on lambda, just like up here in this proposition. And when capital D is negative 1 to the lambda times little when capital D is negative 1 to the lambda times little l mod 4, it will also depend not only on lambda, but on chi sub d evaluated at 2, which we understand. We know what, hang on a second, something's not right. Because chi sub d of 2 shouldn't be defined at, chi sub d shouldn't be defined at 2, right? Let me just get my actual notes and make sure I didn't say something stupid there. Where is it? Okay, I went past it. It's hard to figure out where I wrote some of this stuff down. Let's see. Where is that theorem? I don't actually see where I wrote this down. Let me actually pull the book up. I should be pulled up right to that page in the book. Bear with me for just a moment, because that doesn't make sense to me. Maybe it's higher up than I realize. Okay, so there's some, I can't find it and I'm not gonna waste a bunch of time, but there is some typo there. I will circle it and fix it in the notes and send it out today. Something's wrong here. Okay. But whatever it's supposed to be, I mean, I can just describe it alternatively like this. This guy, this coefficient that we're after will not just be this twisted L function times a factor depending on lambda, which is k minus 1 over 2, but it will also depend if capital D satisfies a certain equivalence mod 4. It will also depend on some expression which is 1 if this -1 to the lambda times little l is 1 mod 8, and -1 if this -1 to the lambda times l is 5 mod 8. Okay. So in other words, these coefficients are completely understood in terms of twisted L functions, maybe times some constants, but we at least understand what those constants depend on in terms of discriminants of the corresponding number fields. Okay. And it might bother you that there's like 2 Eisenstein series. Is there a way to sort of combine these and get one really nice Eisenstein series in some sense of the word nice? And remarkably, the answer is yes. And that will be the following proposition. Let lambda be k minus 1 over 2, just like before. We'll assume that's bigger than or equal to 2 as well. Define h sub k over 2 now to be the following linear combination of e sub k over 2 and f sub k over 2. You're going to take the zeta function evaluated at 1 minus 2 lambda, and you're going to multiply it by the following parenthetical, e sub k over 2 plus 1 plus I to the k times 2 to the negative k over 2 times f sub k over 2. It turns out that's a modular form. Well, it's easy to see because of how spaces of modular forms work. They're vector spaces, that this is a half integer weight k over 2 for big gamma naught tilde of 4, of course. But more crucially, we understand the coefficients of this guy. Here's what they are. If capital D is -1 to the lambda times little l, or -1 to the lambda times 4l, with L bigger than 0, and that's the discriminant of some quadratic number field, and chi sub D is the same associated Dirichlet character as before, then we can actually get a handle on the capital DQ coefficients of h sub k over 2. And those coefficients are just this twisted L function, L of chi sub D at 1 minus lambda. Pay attention to this. Up here, what did we have for e sub k over 2 and f sub k over 2? We didn't have that. We had that same L function at that same value, 1 minus lambda, but we had times a factor with a kind of complicated set of dependencies. What I'm saying here is that this special, like super Eisenstein modular form, its D coefficient is just the L function evaluated at 1 minus lambda. In other words, there is no times a factor depending on this garbage. There's no times a factor. The factor is 1. The coefficient is just this L function evaluated at 1 minus lambda. So I even wrote here, yeah, it looks like I wrote here. You can, in other words, you can ditch the extra factor from the previous theorem for this big H here. Okay. And that's probably just as good as of a place as any to stop. Let me give you a little bit of a preview of coming attractions. We have one more tiny knowledge-based section, I promise. I got to tell you just a little bit about heck operators at half integer weight. As you can see, I've managed to distill that down to about a page and a half. Okay. And then we're gonna, and then the last section is we get back to the congruent number problem and we attack it pretty hard with everything we've learned. Okay. So thank you all for coming again. I'm going to stop recording, and as usual, you can I'll take questions in the same way. You can unmute yourself, or you can type them out in chat, whatever